to see if I could actually get down to the temperature where we expected nuclear spin ordering in solid helium-3. So I'd measured the melting pressure itself as a function of temperature down to 2.7 millidegrees, and below that we could sort of estimate what the melting pressure should do. And so I could use the melting pressure as a thermometer. And so the idea is to see how cold I can get, and this is that data. So this is basically pressure vertically versus time. So I'm adding helium-4 to that upper bellows at a very constant rate, and the system is cooling. This is on November 24th, 1971. Here, I rebalance the capacitance bridge that reads the pressure, and so this is not heating, this is just rebalancing, and then it continues to cool. And then at this point that I later labeled as A, I saw a very sharp decrease in the rate of cooling, and of course I was very unhappy to see that. It suggested that probably the metal bellows had started pushing on some solid helium-3 because we didn't control where the solid helium-3 sat. And so this basically, I terminated this run. This was two interesting things. First of all, I'd started at a temperature of 22 millikelvin, and the dilution refrigerator was capable of actually cooling the helium-3 to 15 millikelvin. This was also the day before Thanksgiving, 1971. I don't know if you celebrate, no Thanksgiving? No? Okay, all right. Well, you probably know it's in November, and it's a 4-day academic holiday because it's on Thursday and then Friday's off and Saturday and Sunday. I must say that Stanford now, in fact, gives students the entire week off. So anyway, so I decided I would pre-cool the apparatus over this 4-day holiday and try again the next Monday. And so here we are, cool, rebalance bridge, cool. And there is that terrible looking decrease in the rate of cooling again. I started at 15 millidegrees, as I'd suggested. And I went back and looked at the pressure where this had occurred before. And it turns out the pressure of this feature had reproduced itself to 2 parts in 100,000. I said, wait a minute, very different starting conditions, extremely unlikely that this could be just some chance heating event. It's much more likely that this is, in fact, the signature of some highly reproducible phase transition inside this mixture of liquid and solid helium-3 at a toasty temperature of about 2.6 thousandths of a degree. And as I say this, the hair stands up on the back of my neck. This was, in fact, a very exciting moment for me. And so, in fact, this was pretty exciting. We decided to study this, but how to do that wasn't clear. We had a mixture of liquid and solid helium-3. Was the transition in the liquid or was the transition in the solid? I mean, we certainly weren't expecting a transition in the liquid, not after John Wheatley's work. So eventually I went to talk to a chemist named Michael Fisher. And Michael Fisher, I asked him how solid helium-3 would grow inside a Pomeranchuk cell, and he said, well, okay, so you have to worry about the surface tension between the liquid and the solid, and that will prevent nucleation of solid helium-3. So you probably would have solid growing on the walls of your sample chamber somewhere, and if you're lucky, maybe only in a couple of places. So then I thought about how I could use that to differentiate between these two signals, and I said, okay, I'm going to, my NMR field, the static field, I'm going to make it larger at the bottom than at the top. So then if I apply a single NMR frequency, usually radio frequency, I can only get resonance in a very thin layer where the magnetic field is the appropriate value for that frequency. And then if I scan this frequency upward, this resonant layer will move downward and vice versa. This, in fact, is the first known example, known by me and most other people, of what became known as MRI. It's just in one dimension, but actually I met Paul Lauterbur, and I asked Paul Lauterbur if he'd actually read our paper, which I published in 1972, and he said yes, he read it when it came out. He started doing his work in 1973. So unfortunately he's dead, so I can't ask him if in fact my very crude thing had influenced him or not. But anyway, so this was the idea, and so this is what typical data looked like. So it basically should have been flat atop across the top, but in fact, the pressure transducer was slightly magnetic, and that's why you get this little blip here. So that we're starting at 28 millikelvin with all liquid sample, and then I start forming solid. The solid has a much larger NMR signal than the liquid does, and so these peaks are solid, and as I continue cooling, in fact, the size of those peaks gets larger and larger. Here I have to keep changing the gain of the strip chart recorder paper, and now the liquid signal looks like it's getting smaller, but it's actually staying at the same size. Just the solid peaks are getting enormous. So this is at about temperature just a little below 3 milledegrees above the temperature of these two transitions, and you can see the liquid signal is nice and flat. So this is real data now. So now it's real data, but I've turned it upside down. So in fact, now time is increasing to the left and pressure is increasing downward. This is the B transition, and we're sweeping the frequency from low to high, high to low. So this structure is the time reversed version of this structure here, but you can see the liquid signal here. It isn't flat across. It, in fact, looks rather badly distorted, so I was very concerned about that. And so here I followed it some more, and then we go through the B transition, and suddenly the liquid signal, that is this thing, which is 2 units high, drops down to less than 1 unit. So it turns out you see very similar drops in all of these solid peaks, but for the solid, this is a change of about 1 to 2% of the total signal. In the liquid, this is over 50%. So I wrote in my lab notebook that night, this is actually April 20th, 2:40 in the morning. This is a wonderful time to do research. Have discovered the BCS transition in liquid helium-3 tonight. And then I explained here what I explained to you. This was so exciting. I went around the entire physics building to share this good news with some of my comrade graduate students. The basement of Clark Hall is very large. Turns out, though, there was not a soul in the basement of Clark Hall. I got desperate and went up to the 5th and 6th floors. It's kind of interesting. Theorists always take the top floors because that way they're closer to God. So anyway, I went up to see if a graduate student had fallen asleep at his desk. I was the only person in the entire physics building that night. So in desperation, at 4 in the morning, I called up David Lee, my thesis advisor, with a great deal of trepidation, I should say. And so I explained to him what I'd seen, and then he agreed. It sounded, my explanation was quite plausible. He didn't get back to sleep. At 6 a.m., he called me back for more details. Anyway, so this was actually, I would say, the most exciting moment of my life. Anyway, so then we actually continued studying solid this B transition. We still thought that the A transition was in the solid, though. And eventually Dave said, well, if the A transition is in the solid, the NMR properties of the solid should change at the A transition. So we should see something. And so this little red signal is what the all-liquid signal looked like, NMR signal. This is absorption as a function of frequency. And just above the temperature of the A transition, we had this huge thing, and most of this is solid. So what we expected was that the solid signal would move to the right, and the liquid signal would sit where it had been, so we'd see the liquid signal. What we found happened was exactly the opposite. The solid didn't move at all, the liquid moved. And as we cooled, it moved more, further and further and further. And then finally, when we saw the B transition, that little drop in pressure, this thing disappeared as it ran back underneath the solid. This was so bizarre that there's not a word in my lab notebook talking about this. But it was very clear that both of these transitions were in the liquid. So I won't go on, but in fact, there was another person then that got involved in this, and that is Tony Leggett.